Hi everyone, my name is Alagappan and I am a PhD candidate at the University of California, Irvine. In this talk, I'll be discussing how Starlink satellite network performed during the solar superstorm of May 2024. Let's start by understanding the phenomenon of solar superstorms. A solar superstorm is an extreme space weather event resulting from massive eruptions in the sun, particularly coronal mass ejections or CMEs. During a CME, the sun ejects plasma and magnetic fields into the space at high speeds, and when these charged particles reach the Earth, they interact with our planet's magnetosphere, potentially causing geomagnetic storms. The Disturbance Storm Time Index, or the DST index, is a measure of geomagnetic storms intensity based on variations in the Earth's magnetic field, and it is typically measured in nanoteslas. Now, satellites are directly exposed, and solar storms can affect satellites in many ways. Now, how do these storms impact the satellites? First, we have the erosion of surface materials, where exposure to the solar storm can alter the physical and optical properties of spacecraft materials. However, LEO satellites have surface protection, typically lasting for around 5 years. Next, we have the electronic damages, where solar storms can cause a buildup of electrons, which can discharge as a small lightning strike and damage electronics. Next, we have the increased atmospheric drag. So, atmospheric drag is the frictional force experienced by objects moving through the atmosphere. And during a solar storm, the Earth's upper atmosphere heats up, causing it to expand. At lower altitudes, where LEO satellites orbit, the satellites experience higher drag due to the higher atmospheric density. This leads to the impact on their positions and orbits as seen in the figure. But what about the network impact on LEO satellite communications? This hasn't been studied before, and understanding these effects becomes crucial as we begin to rely more on satellite networks for global communications. Now, let's review a few prior storms to put the May 2024 superstorm into perspective. First, we have the 1859 Carrington event, which was the most intense storm in record history, with the DST index estimated between -850 and -1750 nanoteslas. For context, DST values below -250 nanoteslas are considered severe. Other storms include the May 1989 storm with a peak DST of -589 nanoteslas and the February 2022 storm with a peak DST of -66 nanoteslas, which also resulted in the loss of 22 satellites. These satellite losses, however, were due to the relatively low orbits of the newly launched satellites, which were still in the process of being raised. In contrast, the May 2024 storm was the largest in the 21st century, with a peak DST of -412 nanoteslas. It extended from May 10th to May 12th, peaking on May 11th and caused widespread geomagnetic disturbances. While not the most severe storm in history, the May 2024 event is significant because it allowed us to observe and analyze the performance of satellite networks like Starlink under extreme space weather conditions. Now, the primary goal of this work was to analyze how Starlink's satellite network performed during the May 2024 solar superstorm. Towards that, we collected data from 81 measurement probes connected to Starlink, which is AS144593, and distributed across various geographical regions as shown in this figure. These probes are part of the Starlink RIPE Atlas network, which provides a global platform for active internet measurements, and we focus on the inbuilt mapping measurements to multiple destinations, such as the root servers that run every 4 minutes on each of these probes. The data collection period was from May 1 to May 15, 2024, allowing us to capture the network performance before, during, and after the solar storm. Now, for this, we analyzed two primary metrics. First is the packet loss rates, where we compared the packet loss rates during the storm to the baseline levels established from May 5th to May 9th, which were the pre-storm days. Next, we have the RTT, or the round trip time measurements, where we measured the latency and normalized it against the minimum observed RTTs for each probe to account for inherent differences in the network paths. Quantify the impact of network performance. For each probe, we define three levels of impact based on loss and latency with respect to the baseline. The high impact are the red probes with the loss rates 10 times or more than the baseline or latency inflation greater than 1.15 times the baseline. Medium impact are orange probes with loss rates 5 to 10 times or latency between 1.075 to 1.15 times, and low impact or green probes which had a minimal change in network performance. Now, based on these three impact levels, the following image displays the probes color-coded accordingly. In short, we had 17 probes that showed high impact and 21 probes with a medium impact. Next, let's examine the impact of packet loss in detail. We plotted the loss percentage, that is the fraction of packets lost relative to the total number of packets sent on the y-axis against each day on the x-axis. The baseline, as mentioned earlier, is computed from the data collected between May 5th and May 9th. On May 10th, the start of the storm, we observed that the loss percentage remained close to the baseline levels. However, on May 11th, coinciding with the storm's peak, the mean packet loss increased by 27%. By May 12th, the end of the storm, we saw the loss percentage returning to values closer to the baseline. Importantly, it's worth noting that majority of the probes experienced minimal increases in packet loss, demonstrating a level of resilience of the Starlink network. Now let's explore the impacts on latencies. For this, we examined the normalized RTTs, which is the RTTs normalized based on the overall minimum observed RTT for each probe destination pair. Using this data, we generated a box and whisker plot as shown in this figure with normalized RTT on the y-axis and the dates on the x-axis. The box represents the interquartile range and the whiskers represent the min and max excluding outliers. The baseline again was calculated from data collected between May 5th and May 9th. On May 11th, the day of the storm's peak, we observed that the mean normalized RTT increased by 8.9% over the baseline. However, unlike the immediate impact seen in packet loss, the maximum increase in latency was seen a day later on May 12th, where the mean normalized RTT rose by 9.15% over the baseline. To investigate further, we scrutinized the changes at a 1 hour granularity, and we found that the peak normalized RTT per hour occurred 14 hours after the storm's peak. This suggests a delayed impact on latency, and one possible explanation is the increased atmospheric drag during the storm, which led to higher satellite orbits being affected and thus higher latency. Next, we consider three specific probes to take a closer look at their performance in terms of packet loss and latency metrics. These probes are one in Canada and France, marked as highly impacted or red probes, and one in Germany, classified as a medium impact or an orange probe. For these plots, we analyze the DST index, the total packet loss, and the normalized RTTs using 1 hour windows, and each observation point represents the mean of all measurements within the 1 hour window. In this talk, I'll discuss specifically about the probe in Canada represented by the blue line, which experienced the worst impact amongst all the probes. This probe experienced a significant increase in packet loss that spiked around the storm's peak, and subsequently we also observed that we observed increased RTTs peaking at approximately 9 times over the baseline. Moreover, the latency performance did not improve even 2 days after the storm's peak. It is worth noting that while the packet losses were immediate, the peak latency occurred at 4 a.m., 2 hours after the storm's peak. So, bringing all our findings together, we conclude that despite the storm's severity, Starlink weathered the storm relatively well. While there were increases in packet loss and latency, the network continued to function, indicating a level of inherent resilience in the system. We observed that packet losses spiked immediately during the storm, whereas the increases in latency were delayed and persistent. This delayed increase in latency is possibly due to the increased atmospheric drag experienced during the storm. Now, while this was a significant storm, it wasn't the most severe possible, and several research questions remain open. How does atmospheric drag correlate with loss and latency, and why is the impact on latency delayed? Next, how do solar storms at other scales affect satellite network performance? For instance, at a smaller scale or at Carrington scale events. Next, can we develop models that accurately forecast the network impact of solar storms? And finally, can we design mitigation strategies to minimize the network impact? Addressing these questions is essential for enhancing the reliability and resilience of satellite networks in the face of space weather challenges. Thank you for listening to my talk.